Today, I'm going to show you our 4-quadrant amplifier and the microgrid test bench in which the amplifier is located. To begin with, let me remind you the PHIL concept. Power hardware in the loop is an extension of hardware in the loop in which the real-time simulation environment is capable of exchanging power with external devices under test. These DUTs are connected to the simulation using a power amplifier, and this power amplifier is controlled by the simulation. Universities around the world are rapidly adopting PHIL technologies, which is a significant benefit for their researchers and students. However, the time, the cost, and the complexity to build such test benches is very high. It remains a challenge. This is the reason why OPAL-RT developed the OP1420 Power Hardware in the Loop Microgrid Test Bench. It is a turnkey platform which is modular, flexible, and highly reconfigurable. It is an ideal simulation platform which allows users to do hands-on experiments by testing external components under various operating conditions. We can mention a few applications, such as testing microgrid controllers and protection systems, AC and DC microgrid simulation with external DER and nonlinear loads, and integration of microgrid within large power systems. Components such as Lucas Noulet test benches presented by Fabian previously can easily be connected to this test bench. We could think about having PV panel connected to group 1 of this test bench, a storage system able to source and sync power connected to group 2, and a DC network emulation connected to group 3, which makes this test bench highly scalable and configurable. I think now it's time to have a deeper look at each component of this test bench by looking at the OP1420 PHIL microgrid test bench in University Duisburg-Essen laboratory. This safety box provides low voltage supply to other components and controls the three-phase input power on the front side. It also allows to disconnect DC sources and high power components of the test bench in case of fault. The OP5707 real-time simulator allows to run power system models in real time over several CPU cores. This OP5707 real-time simulator is composed by Intel Xeon CPU cores, which allows to run the simulation in real time, and you can exchange information with external controllers using analog and digital input-output boards. These I/O boards are directly managed by a Xilinx Vertex 7 FPGA board. As you can see here, you also have an optical connectivity, which is a high-speed, low-latency communication link with the power amplifier. It is required to ensure stability of the PHIL system. The models running in this real-time simulator are designed using MATLAB Simulink, and RTLab software Artemis solver from OPAL-RT ensures the real-time constraints to be respected by having a computation time lower than the time step and decoupling the power system model on several CPU cores. OPAL-RT developed some special blocks which are integrated in RTLab library within MATLAB Simulink toolbox, which allows to send voltage and current set points from the simulation to the power amplifier and receive measurements from the amplifier to the simulator. This set point can be sent from the CPU, but you will be limited by the CPU time step. So if you have running power system model at 50 microseconds, only 1 point every 50 microseconds can be sent from the simulator to the amplifier. For high frequencies, higher than 1 or 2 kilohertz, we highly advise using the FPGA generation to send set points. You will benefit from a higher resolution thanks to the FPGA clock. Microgrid models are provided by OPAL-RT. They are composed by wind turbine, battery energy storage system, PV plant, diesel generator, aggregated loads, even microgrid controllers. You could replace the PV panel simulated by the Lucas-Noulet PV test bench as presented previously by Fabian in the model, and the result of these PHIL experiments can be directly displayed within a LabVIEW panel composed by scopes, graphs, widgets, sliders, and the operator can directly communicate with this simulation on the fly. We can switch now to this microgrid busbar panel. It is composed by padlockable connector disconnectors, which allows to manually connect external DER to the internal bus bar. This actuator push button allows the contactor to close to have the physical connection of this DER to the bus bar. Each DER is composed by 4 banana plug connectors for the 3 phases and the neutral. And there is a selector here, selector button. If it's set to local, then the connection of external DER to the internal bus bar can be done with this push button actuator. If it's remote, then the user can remotely control the external DER connection directly from the model by using a digital signal sent from the model to the microgrid bus bar. Interesting component, the power meter panel allows measurements to be displayed on the fly, such as voltage, current, active power, reactive power, apparent power, power factor, total harmonic distortion. And we can benefit from these measurements thanks to current transformer and potential transformers connected to the 4 microgrid busbar DER connections. Let's switch to the heart of this test bench with the OP8110 4-quadrant power hardware-in-the-loop amplifier. This one is composed by 2 groups of 3-phase amplifiers, while this one is composed by 1 group of 3-phase. So each group has 5 kilowatts, and it can be operated in AC mode, DC mode, voltage mode, and current mode as well. In terms of performance, the innovative technology based on soft switching cells with silicon carbide transistors is used, which allows to have no dissipation and an energy efficiency higher than 96%. In terms of fidelity, the bandwidth is up to 10 kilohertz at -3 decibel, and total harmonic distortion lower than 0.5%. In terms of safety, we have, for example, overvoltage, overcurrent, undervoltage, short circuits, and over-temperature protections. In terms of connectivity, optical fiber links are connected between these power amplifiers and the real-time simulator. It uses small form factor pluggable connectors, and to ensure a very fast communication, Aurora communication protocol is implemented within the simulator FPGA and within the power amplifier FPGA. So we have a communication higher than 5 gigabits per second, which is key to ensure the stability of the power hardware in the loop setup. Finally, we have here 3 DC sources of 6 kilowatt, 500 volt DC. Each of them are controlling 1 group of three-phase power amplifier to sink and source power. It concludes the presentation of the OP1420 PHIL microgrid test bench. And with that, I would like to give the floor to Mark, who is going to present a live PHIL experiment.